Okay, we're on section 5.3 today. We've now in section 5, chapter 5, done some simulations. So we talked about a simulation and gathering information from a population and seeing what happens when you take these simulations. So we talked a little bit in class on Monday or Tuesday, about sample size, how that affects what the distribution looks like, as well as maybe what it looked like before we started. So I'm going to jump around here a little bit. Sorry, my screens are off. I got them in different orders. But the first thing we want to do is just kind of generalize what we learned. So there's actually a theorem called the central limit theorem, which is one of the few theorems you have to actually know by name in this class. And the central limit theorem basically tells us what the shape of a sampling distribution is going to look like. So the theorem says the shape of the sampling distribution will be approximately normal. Sorry, there should be a little extra thing there. If the population is normal. So in other words, if we start with a normal population, the sampling distribution is going to be normal, okay? But more importantly, because we won't always know what that population is going to be like this rectangle problem we did, which was not normal, but notice when we did those problems, the sampling distribution actually did look kind of normal. So for other populations, the sampling distribution will become normal, the more normal as the sample size increases. So in other words, the bigger the sample size, the more roughly normal the sampling distribution will be. It's a pretty powerful thing. We kind of saw it with the rectangles because now we don't have to worry about what the population looks like to know that the sampling distribution is going to be normal, because we've learned a lot of stuff about the normal curve that we will continue to learn as we go. So that's kind of the basic idea of what the central limit theorem is. And then more importantly than that, what happens? So what other properties does the sampling distribution have? So first of all, notice I'm using this term, the sampling distribution. This means all possible samples of a given size. So when we did the simulation in class, we just each did a certain amount of simulations or a certain amount of samples, right? And we just simulated it. We did a lot, but we didn't do all of them. If we had done all of those rectangle problems, we would have done 100, choose 5. I might have already said this in class. I apologize if I have. But if I go 100, choose 5, 75 million different samples. Clearly, we're not going to do that. However, if we did, we know what's going to happen. Computers could do that for us, first of all, pretty easily, right? So here are the properties that are pretty important. They're going to help us start to answer questions then about samples. Right. So what we're doing here is we're taking a random sample of size n from a population that has a specific mean and a specific standard deviation. Remember, in these problems, we're going to know what that mean and that standard deviation are, even though in the real world, we would never really know that. And that's what's going to come in the later chapters 7, 8, 9, and 10. So right now, we're just looking at populations that we do know. So we're going to take a sample of size n, make this distribution. What's going to happen? So the first thing that's going to happen is the mean of the sampling distribution is going to be equal to the mean of the population, okay? The mean of the sampling distribution will be exactly equal to the mean of the population. We saw it get close in our sample, I hope, in our rectangles. We always do every year. But if we took all of them, it would be the same, okay? The way we write that, this little notation here, mean of x bar means mean of the sampling distribution. Kind of wrote that up right there, but just so we can shorthand it, the mean of the sampling distribution will be equal to the mean of the population. We also learned that the bigger the sample size, the more squished my distribution, the more normal it becomes and the more squished it becomes. So there's a relationship for standard deviation also. So the standard deviation of the sampling distribution, which we sometimes call standard error. So we're going to bounce these terms back a little bit. We should always call it standard error, but sometimes I'll just forget and call it standard deviation. But we'll always be talking about whether we're talking about the population or the distribution, okay? So we'll call it a standard error is the sampling distribution's standard deviation. It equals the standard deviation of the population divided by the square root of the sample size. So you can see the bigger the sample size, the bigger that number is, the smaller that number is, right? So the distribution becomes more squished. So the cool thing is now is I can say, hey, let's take a sample from a population and see what we expect to happen. And that's what's going to come next. Before we do that, real quick, not a super important thing here, but kind of a quick thing. It's always an interesting idea is how big a sample should we really have to take in statistics? And we're not going to spend a ton of time with this in this class, but it's an interesting fact to know that as long as your sample size is small compared to the population, and small we usually say less than 10%, then it doesn't really matter how big your sample is. As long as it's bigger than 30, we're going to talk more about that later. 30 is a pretty magic number. If the population is normal in the first place, then that 30 is not going to matter. But if it isn't normal, which we will never know, 30 is kind of a fail-safe to make sure it will be close enough to normal to use those properties. So the cool thing is it doesn't really matter. We could take a lot more, and it doesn't really help us. It doesn't get a whole lot closer for most people's purposes. If you're trying to be super, super precise, then maybe. And actually, mathematicians will say it's better to be a little bit smaller because then there's less chance of the people in your sample having some dependency on each other. In other words, if I took a sample too big, I might get same family members or people that are married or something like that. That might be some sort of dependency in what the question I'm asking. Might not matter depending on the question I'm asking, but it might. So typically we don't have to get super big, which is really cool. In a year of a presidential election right now, there's lots of polls out there. Typically, they don't take any more than 1,000, which is pretty small compared to the population, but usually tells us a lot. So let's just kind of put all this together and do it into a question, maybe, so you can see what kind of question is going to happen. And here's the basic question that you're going to see. Let's do two things. Hang on a second here. Sorry. Let's recover that up right here. So we're going to take this problem that was the average, the number of children per family that we've been using in this chapter a little bit. So I'll write it up so you can see what I'm doing here. So the population has a mean of 0.916 and a standard deviation of 1.1. So that's the population. And here's what we're going to do. We're going to take a random sample of 20 families, okay? 20 families. And we're also going to say, sorry, that the population is roughly normal for now, just so we can use that. We're going to say that pretty much on all our problems, that the population is roughly normal. And typically for a number of children, it kind of is. It's a little bit skewed right for sure. But once we take the sampling distribution, it'll become close enough for us to do it. So the question now is, what's the probability that a random sample of 20 families has an average of 1.5 children or fewer? So remember, a quick little normal review problem. If I was just asking you a normal curve problem, 916, 1.11, and I ask you what's the probability that any one family had less than 2, we would just do this little normal curve thing, right? So all we need to do in these problems is find the proper normal curve with the proper mean and the proper standard deviation. Remember, we're not picking one, though. We're picking a sample of 20. So when I redraw this picture, this is now what I will call my sampling distribution. Okay, my sampling distribution is roughly normal. The sampling distribution is going to have the same mean as the population, 0.916. So this is the mean of X bar now, the mean of the sampling distribution. However, its standard deviation is going to be the standard deviation of the population divided by the square root of the sample size. So it's still a distribution, it's still normal. However, the standard deviation has changed. And the question is, what's the probability of having an average of 1.5 or fewer? So there is 1.5, and we find that area. I'm hoping I have shown you this on the calculator. So remember, there's a z-score here, 1.5 minus 0.916 over the standard deviation, 1.11 divided by the square root of 20, and then you go to your chart. However, hopefully we've talked about the calculator, so we can do this thing called normal CDF. We're going from negative infinity is my low end, all the way up to 1.5 with a standard deviation of 0.916. Sorry, it's not going to fit. 1.11 divided by the square root of 20. I can do that math real quick. Normal CDF from negative infinity to 1.5 with a mean of 0.916 and a standard deviation of 1.11 divided by the square root of 20. And I get 99%. Remember that over 50% of our families had 0, so it's not an unusual answer to have an average of 20 to be pretty high, right? An average of 20 people's 1.5 or lower, 1.5 or lower is going to be a pretty high probability of that. Okay. So then we can ask all the regular normal curve questions that I would have asked before. We've reviewed a lot of those. Now that we have the mean and the standard deviation, that's all we have to do. So the next question, this one, we're going to skip that one for just a second. Hang tight on that one. What average number of children are reasonably likely in a random sample of size 20? So I'm going to erase this, so you can pause it and look at it if you need to. And now we're going to do We're going to do the same basic thing. We're going to draw a curve. Okay, this is a sampling distribution now. 0.916, standard deviation is 1.11 divided by the square root of 20. Question is, which ones are reasonably likely? Reasonably likely means the middle 95%. And those have z-scores of 1.96 and negative 1.96. So we could do the same thing. We could find those areas, which we know, I guess, are 0.025. We already did that. Sorry, never mind. So we go plus or minus 1.96 equals x minus the mean, 0.916 divided by the standard deviation. We could solve this twice. However, we could also use inverse norm, right? Inverse norm of 0.025 with a mean of 0.916 and a standard deviation of 1.11 divided by the square root of 20. So we go inverse norm, 0.025 with a mean of 0.916 and a standard deviation of 1.11 divided by the square root of 20. Uh-oh, got a little problem. All right, sorry about that. I'm going to do that one more time. Inverse norm, I'll get it. 0.025. There we go. No, what is going on? I do know what I'm doing. One last try, sorry. No, I didn't like it again. All right, sorry about this. One day I'll learn how to pause that machine over there. We'll go inverse norm. I'll get it. What's happening, just so you know, is I'm pasting it in the wrong place. Just got to be a little bit careful about where you paste it. Inverse norm. All right, never mind. I'm going to draw my other calculator out of the newer version of the calculator. I knew what I was doing. Clearly, I don't. Here we go. 0.025 with a mean of 0.916. Sorry about that stalling there. 1.11 divided by the square root of 20. And I get 42.4295. So that's that number right there, right? The 0.4295. And then the other one, I could just use symmetry if I want, or I could do inverse norm of 0.975. All right, one last problem. And that last problem is, instead of asking for average, they ask for total number of children. So all my answer questions so far have been, what's the probability of getting a certain average? But now the question says, what's the probability there are 30 or fewer children? I'm going to come down here. So you can see there's actually two methods. So let me rewrite this. So probability of 30 or fewer in a sample of 20. So there's two ways to do this. One is probably the way most people would do it, because I haven't told you the second way, is just to change this to average, right? So 30 or fewer in a sample of 20 is just an average of less than 30 divided by 20, or 1.5. So what I would say is method one is just find the equivalent average. I don't really want you to do it this way because this is not going to work in the long run. We're just going to change it to totals. We're just going to get a new distribution. It's kind of cool. So it turns out that if you do totals, you get a distribution, but the new mean is going to be the old mean times your sample size, right? Because that's how you find average, is we divided by that sample size to get average. I did 30 divided by 20, so I'm just going to undo that. So the question was, the old mean was, now I forgot what the old mean was, 1.11. Let me go back and get it, sorry. No, 0.916. Good thing I went back and checked. 0.916. These are the mean and standard deviation of the population. So when I do a total now, so this would be total instead of average, this is going to be 0.916 times 20. That's how many we would expect on average, right? And then the standard deviation now turns out to be the standard deviation of the population times the square root of the sample size instead of divided by. I show you the little math there as to why. All you got to do is take the old standard deviation and multiply it by n. You might remember that from chapter 2. If you multiply every number in a data set by the same thing, or in this case by the sample size, you change the standard deviation by the same factor. So my new standard deviation would be 1.11 times the square root of 20. And now I'm looking for 30 or 30 or less. Don't worry about this right now. So we're going to go normal CDF. From negative infinity to 30 with a mean of 0.916 times 20 and a standard deviation of 1.11 times the square root of 20. It's a little bit more work than the averages at the beginning, but you got to do this because later on we're going to have problems set up for this way that you can't revert back. So we're going to go normal CDF from negative infinity to 30 with a mean of 0.916 times 20. And the standard deviation of 1.11 times the square root of 20. And we're going to get that 99.06. Right. So I know that's a lot. We'll review a lot of this for sure and practice in class, but hopefully that's enough to get you going.